Welcome to Lecture 4.7 on antiderivatives for Calculus 1. Integrals, the antiderivative. Most math functions have inverse functions, which simply undo what the function does. This is nothing new, and we already understand this. For example, addition and subtraction are inverse functions. If you add to, the way you undo adding to is you subtract to. Again, very intuitive. This is what we've grown up with all our lives with beginning, counting, etc. As are the functions multiplication and division. If you multiply by 2, the opposite of that, or the way to undo it, is to divide by 2. So an integral is simply the antiderivative, or the inverse function of a derivative. An integral undoes a derivative. So let's look at an example here. So if we have a function x squared plus 4, this is a very simple derivative that you should know how to find very quickly now. The derivative equals 2x, right? The derivative of x squared, we simply pull the exponent down in front, subtract 1 from the exponent. We take the derivative of the next part because we take each part of a sum separately, and the derivative of any constant is 0, so our derivative is just 2x. So if we're taking the integral, and that's what this sign is, and we'll look at that in a minute with some vocabulary, the integral of 2x and dx, and this is the dx is just telling us that we're integrating the function with respect to x. This is not a variable. This d is not a variable. It's telling us that we're integrating this derivative with respect to x. Okay, so we're integrating, we're undoing the derivative, and so we get x squared. Now notice there's a plus c here. Now why is that? Well, let's look at another example. What if we had the function x squared plus 8? Well, notice the derivative is also 2x. So the integral of 2x isn't just x squared, because that's not the original function. It's plus some original constant, and we don't know what that constant necessarily is just by giving this integral, by giving us the derivative here. And so you can see here that the constant in the first function is plus 4. The constant in the second function, the c, would equal positive 8, and the constant in the third function would equal negative 4. So when we're taking an integral of a function, we always add plus c to the end, because we don't know if there are any constants being added to this original function, because again, the derivative of a constant is always 0. So when you're taking an integral, you always have to add the plus c at the end. Many problems will give you information about the function, like maybe a point or something, and so you can figure out, based upon this original function, what the value of c is, and we'll look at that. Okay. So integration is what we call the process of finding an integral or antiderivative, just like sum is the process of doing addition. An indefinite integral is when you find a formula or a function without values. That's what we did on the previous page. Okay, we didn't find a number, we found a formula, x squared plus c. This is the integral sign, and the integrand is what we're integrating. In the last example, it was 2x. And you can see here, so the integrand in this integral here is 2x. It's just the function that we're integrating or finding the antiderivative for. So one of the nice parts here is that since we've been working with derivatives for a while, working with integrals should be a little bit familiar, or somewhat familiar, because we're just going the opposite direction. And many of the same rules apply. Okay? So if we have a constant times a function, the integral of the antiderivative is a constant times the antiderivative of the function. So we can still pull the constant out in front. Sums and differences of functions, we can still take each part and add or subtract them. Here's a new one here. When we have a power function, a function raised to a power, the way to undo that is the antiderivative will be the exponent minus 1. No, I'm sorry, that's a plus. The exponent plus 1 over the exponent plus 1. So before, remember, when we took the derivative, we just put the exponent down in front and then subtracted 1. So now we take the exponent, put it in the denominator and add 1 to it, and also add 1 to the exponent, the original exponent. Okay, and once you do a couple examples, it'll get a little bit easier to see. Okay, if the function is 1 over x, the integral of this, or the antiderivative, is the natural log of x. And the reason this is in absolute values, remember, you cannot take a log of a negative number. So if this was x squared, for example, you wouldn't need the absolute value because every value squared is going to be positive. As we saw before with the Euler's constant, e to the x, the derivative is e to the x, so the integral is the same. Cosine, the antiderivative or integral of sine x. The integral of sine x is negative cosine. Again, these are just the opposite values that we saw in previous sections. Okay, so I'm not going to walk through these. You do need to be familiar with these. Probably some of the more difficult are the inverse trig functions and also these hyperbolic trig functions. So you need to know this table. You need to memorize this table. So let's look at some simple examples with the power rule. Okay, just so we kind of start getting our feet wet and start practicing antiderivatives. So again, here we have x cubed, so we have x to the n. Remember, what we're going to do is we're going to bring that exponent down into the denominator, n plus 1. Since our exponent, or our n, is equal to 3, we're going to have 3 plus 1 in the denominator, and our new exponent, or 4. And our new exponent is also going to be 3 plus 1. Okay? Again, we bring that exponent to the denominator, add 1 to it, add 1 to our exponent, so we get 1/4 x to the 4th. And you must add a c here. In doing your homework or doing the test, if you don't add the c, you will get this marked wrong. Now, a simple way, remember, since integrals are antiderivatives or inverse derivatives, a simple way to check our answer is simply to take the derivative of this. Okay? So notice if we take the derivative of this, we pull the 4 down in front. 4 times 1/4 is 1, and we subtract 1 from the exponent, and we get x cubed. Okay? So we can do this even with a radical. Notice that x to the negative 1/2 is actually 1 over the square root of x. Remember that rational exponents are indicators that we have a radical in them. So since it's already in the power form, we're just going to perform using this kind of formula here. So we get 1 over negative 1/2 plus 1. And in the numerator, we get x to the negative 1/2 plus 1. And so this gives us 2x to the 1/2. Okay? And again, plus c. Now, in this last example where we have a radical, usually the easiest thing to do is to convert this into an exponent. And remember, the cube root of x is x to the 1/3. So when we do use the exponent of 1/3, again, we put that in the denominator, plus 1, add 1/3 plus 1. And so we get 4/3 x to the 4/3. Okay? Actually, that's wrong, isn't it? This should be 3/4 x to the, because we have 1 over 4/3, which would be the inverse, which would be 3/4 x to the 4/3. So be careful here. Be careful here. This answer here is incorrect. This 4/3, which is what's in the denominator, since it's 1 over it, we need the inverse, which would be 3/4 x to the 4/3. So sorry for my typo there. Be mindful that this should be 3/4. Okay? Now, what I've done here is I've gone back and put it into radical form. A good practice is to put your answer in whatever form the problem was in the beginning. Okay? You can check your homework as it's doing this. If it leaves it in this form and accepts the answer, great. But if your form was in radical to begin with, you might want to put it back and check the answer that way. And again, remember, we have the plus c. Now, one of the things in algebra, this would have been an unacceptable answer because we would have wanted you to reduce the radical and pull one of the factors of x outside. But in calculus, we often do not have to follow those same rules of algebra because we're moving on to higher concepts. Even like rationalizing the denominator that we had to do in algebra and trigonometry. Okay, so let's look at another problem that's a little more complex. So we have a derivative which is equal to 4 sine x plus a rational expression 2x to the 5th minus the square root of x over x. Now the first thing we want to do here is we actually want to simplify this expression. This first piece, we can take the antiderivative or integral of this piece quite easily. And remember, when it's a sum, we can do each piece separately. So we're going to ignore the 4 sine. Notice there's only one term in the denominator, and it's a term of x. So we can actually separate this into 2 fractions. So we could have 4 sine x plus 2x over 5 over x minus the square root of x over x. Okay? So if I first separate the fraction into 2 fractions, you see it here, then it makes it much easier to reduce. And remember that the square root of x is x to the 1/2. You should know how to reduce these by using exponentials when we're dividing by the same factor. And so ultimately I get 4 sine x plus 2x to the 4th. And here I would have left it not in radical form, but I would have put this back into exponential form, which would have been minus x to the negative 1/2, because we're going to use the power rule to do that piece too. All right. So remember, we pull the constant out in front. The antiderivative, the integral of sine x, is negative cosine x. We pull the constant out in front too. Remember that the exponent goes in the denominator, plus 1, and the new exponent is plus 1. Remember, since this is x to the negative 1/2, we have negative 1/2 plus 1, which is 1/2, and of course negative 1/2 plus 1/2 is, plus 1 is 1/2. So we have this, and let's just do a little cleanup here. And so our final answer here is negative 4 cosine x plus 2/5 x to the 5th minus 2 times the square root of x plus c. Do not forget your plus c. And again, here I would put it back into the radical form simply because it's in radical form here. In the interim step, you want to have it as an exponential so you can solve it. So this was not a good move that we did here. Okay. Now let's look at a word problem and see if we can work through this. Okay. So sales records at Jared's Technology show that the rate of change of the revenue, that is the marginal revenue in dollars per unit for a motherboard, is equal to 300 minus 0.2x, where x represents the number sold. Find the total revenue for the product, then find the total revenue from the sale of 1,000 motherboards. Now, if you remember, what we're talking about is a rate of change. A rate of change, marginal revenue, hopefully you remember, is the derivative of revenue. So this is the derivative of the revenue function. Since we're looking for the actual total revenue function, we're looking for the antiderivative of marginal revenue. So all we're looking for is the integral of this marginal revenue. Okay? Again, remember that marginal revenue equals the derivative. So our revenue function would equal the integral of marginal revenue, which would equal the integral of that function. Now this is a very simple integral to do. Now be careful here, and this is a very common mistake. We've gotten so used to the derivative of a constant being 0 that a lot of students start making the integral of a constant 0, and this is not true. Remember that the derivative of a constant times x is that constant. So when we have the integral of a constant, this integral is simply that constant times x. And you can see, because the derivative of 300x would be 300. Okay, if we go in reverse, the derivative of 300x would be 300. So the integral of 300 is 300x. So the integrals of constants are easy. You just add the variable at the end as a multiplier. Okay? And here again, we have another exponential function. Do not forget that when you don't see an exponent, the actual exponent is 1. So we get 0.02 over 1 plus 1, or 2. I wish I'd written that here. I'm sorry I didn't. And the new exponent is raised by the power, or adding 1. So 1 plus 1 equals 2. So 0.2 divided by 2 gives us 0.1. So listen to that again. Remember, when there is not an exponent present, when you don't see one, the exponent is 1. So I get 0.2 over 1 plus 1, which is 2. 0.2 divided by 2 is 0.1. And then I add 1 to the exponent. 1 plus 1 is 2. Now do not forget that I have to add a c here. Now this problem is, although it doesn't necessarily give us explicitly the information to calculate c, it gives us that information implicitly. Revenue is the money we make from selling things, right? Revenue is the money you make from selling things, and it tells us that X is the number sold. So it's easy for us to find the value of C if we think about how much money we will make if we don't sell anything. Very intuitive concept, right? If you have a business and you don't sell anything, how much money are you going to get? Zero. So notice that if we sell 0 units, then R of X, our revenue, is going to equal 0. So if we plug in 0 for X and solve for this equaling 0, if we sell 0 units, we make 0 money, we just plug this into the formula, 300 times 0, 300 times 0 minus 0.1 times 0 squared plus C. We can now solve for C, and everything becomes 0 here. So C is actually 0 in this problem. It will not always be. For example, costs might not, the cost of 0 might not be 0 because you might have to pay rent or other things even if you didn't make anything. Okay, so we know that our answer to the first problem, find the total revenue function, is simply this: R of X, the total revenue equals 300X minus 0.1X squared. So the last step is really simple to find. Find the total revenue from the sale of 1,000. So we just plug in 1,000 because X represents the number sold. So all we have to do is plug in that number and we get $200,000. Again, be mindful of the units, be mindful of the concept of the problem. These problems in 4.7 should be relatively simple and straightforward before we move into more complicated integrals in the next chapter.